Hello, everybody. I hope everybody's doing well and you're handling the situation and coping well with this unfortunate situation. And I think at the end of this, hopefully, everything will be better uh, and we'll all come together. Uh, so I starting the our last series of lectures for this course, Make 3850 at Wentworth. And this is our last chapter related to rigid body kinetics, right? And you guys remember from the previous chapter, so this is chapter 17 actually in the Hippler book, right? And you guys remember from chapter 16, previous chapter, when we discussed the rigid body kinematics. Rigid body motion could be one of the three types. It could be a pure translation, when the body is just translating. It could be pure rotation. Now this rotation could be about center of gravity, or it could be about any other axis. Or it's the more interesting type of motion is the general plane motion, which is combination of translation and rotation. Remember, we had a bunch of examples on that, like crank slider mechanism, like the rolling motion, and so on. All right, so I thought to come up with the equations describing the motion here, rather than doing a derivation for you, we'll do more examples, and then I'll just try to see if we could, together come up with the logically with the equations that describes the motion. So basically, I have to mention that actually this chapter only deals with using second law to solve kinetic problems. And we have to modify, obviously, second law, F equal ma, to account for the rotation of the motion. And you guys remember earlier, before the break, when we were meeting in the class, that kinetic problems can be solved using different methods. We could use, second law. We could use, you guys remember, we could use kinetic energy method, which is part work and part relating work to kinetic energy, right? To energy method. And then also impulse and momentum approach. So these are different ways that we could solve kinetic problems. But in this particular video, I just want to concentrate only on the second law. So this is just second law modified slightly to account for rotation. Okay, so I thought maybe we'll we make a table, we divide this into particle equations and rigid body equations, and then we'll try to go back and talk about the equations we had in statics and now what we have in dynamics. So the equations here actually are related to chapter 17, guys, because this is the rigid body dynamics. Okay, so you guys remember in statics, for a two-dimensional, of course, let's just limit our discussion to a two-dimensional case. Sum of the forces in x equals 0, sum of the forces in y equals 0. Obviously, you want to make sure that the body is not translating in the x direction or y direction, or for that in any direction actually. So what happened when in chapter 13, sum of the forces, when we go to dynamics, particle of dynamics, kinetics of particles using second law, sum of the forces is going to be me, mass times acceleration in the x direction. Sum of the forces is mass times sum of the forces in y equal mass times y component of acceleration, F equal ma. And you guys remember that you could also do that for curvilinear motion in nt direction, right? Just change the subscript. All right, then let's look at the rigid body equations that we had in statics. So besides these two equations, sum of the forces in x and y equals 0, remember, rigid body could rotate. So we had another equation. That equation is sum of the moment about any point is equal to 0. In this case, for a two-dimension, that's basically that we are talking about the z-axis passing through that point. So sum of the moment in a way about z-axis is equal to 0. All right, let's now concentrate on chapter 17, which is this. So clearly, sum of the forces in the x direction is going to be max. But there is a problem, guys. When you have a rigid body, right, if it's rotating, right, we are talking about acceleration of what point? Acceleration of this point, this point, this point. Which point? Each point has a different acceleration. Now, it turns out that the important point is actually the center of gravity. So we're talking about acceleration of g, which is typically also denoted by a bar. So bar here means center of gravity. So this is actually acceleration of the center of gravity. Sorry, I had to pause for a second. So I just was talking about the right-hand side of these equations. So we are going to use the acceleration of the center of gravity and break it into x and y. And then the right-hand side would be mass times acceleration of center of gravity in the x direction, and the same thing here. Okay, so then the next question is what happens to this equation, the right-hand side of this equation? So basically, this equation, sum of the moment, if you can take moment about any point, but if you take moment about center of gravity, that becomes basically I sub g times alpha. So you could see the similarities between mass times acceleration, right? Changing to what? Angular acceleration alpha when it comes to rotation, and in a way, the translating mass becomes the rotational mass. I bar is called the mass moment of inertia. It's a property of the mass, and it has to do with the rotation of the bodies, and I'm going to have a video on that pretty soon, talking about this mass moment of inertia. So these are the three equations that we're going to be using in this chapter, as shown here. Let me go to the next page. So here, basically, I say that if you have a body that is translating, and acceleration of the center of mass is denoted by a sub g or a bar, and also rotating with some angular acceleration, our general equations are like this. So summing forces in the x equal to mass times x component of the acceleration of the center of mass. That would be this guy. And then similarly, in the y direction, same thing. So we have to use a bar y. And then if you take moment, that is equal to I bar alpha. To take a moment, or the torque is equal to I bar alpha. And as I said, I'll have a video reviewing this property known as mass moment of inertia, right? But just before we are done with this video, I just wanted to make a note here that if a body is in pure translation, right, what will happen to these three equations here? Well, the body is translating, so we do have acceleration of the center of mass, right? So these two first equations don't change. But this third equation, if you take moment, since alpha is 0, it's not rotating, right? So the right-hand side becomes 0. Similarly, if a body is in pure rotation about its center of mass, so you see now acceleration of the center of mass, a bar or a sub g, is going to be 0 because it's fixed. But the body is rotating with some angular acceleration. So this time, the right-hand side of these two equations becomes 0, as you could see here. But the right-hand side of the equation related to the torque is going to be equal to I alpha. Okay, so thanks for watching and listening. I'll come back to wrap this up by showing you another video related to the mass moment of inertia. And then I have a bunch of examples that I'm going to share it with you soon. Thanks.